Okay, cool. So yeah, welcome to CPSC 14 tutorial 1. Today we're going to be going through some reduced problems. So far, hopefully you've seen a bunch of Erlang from the homework, especially. It's a hard introduction to Erlang, but like a good one. So today we'll be applying some of that Erlang knowledge on some pretty simple reduced problems to get you warmed up for exams and subsequent homeworks. There's 3 problems. They're on Piazza. Hopefully you guys have all seen them. True. So feel free to download that zip file and start on question 1. The first one gives you a sequential version of computing the mean of a list of numbers, which hopefully is familiar. And then it asks you to write a parallel version. Just off the top, make sure that when you download it, you're working with the course library added. Otherwise, like wtree won't work, or like all those functions won't work. Anything related to reduce. If you haven't done that yet, you can clone the course template. Tutorial for 14. Yeah. So feel free to go on Piazza, grab the tutorial 1 zip file, and then make sure you have access to that. Give problem 1 a go. I'll go through it in, I would say, 5 or 10 minutes, depending on how people are doing. If you've already done it, feel free to move on to later questions. Any questions about the first problem? You're from 418?
Sorry?
You here for 418?
Yes.
We have a full house, that's good. There's a chair there, and then hopefully nobody else comes. I'll get a bigger room next week, I just wasn't sure if people would be able to make.
Maybe I should, I'm just thinking about I should maybe go complete my.
Oh,
I will record
Are you-
this.
are you-
I'm
you
recording
are?
it, so if you want to watch it later, you can do that. Yeah, okay.
I'll get on that.
Okay,
Yes.
so,
Thanks.
no worries.
no. Probably come back as well.
Okay.
Finish the homework.
Okay, good. Yeah, I know it's due tonight, it's kind of bad time.
Yeah.
Hopefully other homework's don't align on Mondays.
Yeah. Yeah, really thank you for posting these.
No worries. I hope the recordings can be decent. That's my goal. Last semester they were very good, so I'm hoping to make them just marginally better this semester and then keep. We'll see. Luck on homework. Hopefully you're close.
Yeah, I hope so too.
Michael, what's the key in question one?
The key is for each worker, how you get what data is associated with. So in almost every single reduce problem you ever do, you're gonna have a line like it's gonna be some fun. And you're gonna have data equals W tree get.
Sorry, I'm sorry.
Exactly what it is. Proc state and key, which simply, you don't have to worry about the internals, is the proc state, there's the processor like ID and stuff, if it has children and so on. And the key tells you from like all of the data associated with this problem, so like this full array, which data belongs to me. So you can imagine for this node, it would be 1 and 2.
Okay. Yeah.
So it's how you get the data associated with that node.
Okay.
That's
Kind of a follow-up on this one.
Yeah.
So who decides what key gets assigned to which, is it the internals?
yeah, I mean, you can look at the W-tree reduce implementation, like in the course library. To be honest, I haven't really rolled up my sleeves and gone through it in a lot of depth. But that being said, it's kind of related to W-tree create. So I think, you don't really see an example in the starter, but maybe in the tests. If you look at T1 tests and then to like run mean parallel, you can see W is like a W tree create, like a worker tree of an amount of workers. We update it by putting in the data under some key. Here, the key is literally just data. And then we call the mean parallel. So you can see how they're related. Again, it's probably worthwhile to go through the course library a little bit to understand how these work. But generally speaking, this pattern, you can just kind of remember. And then the problems on too. Your job mostly is to worry about what is the function that each leaf should produce, like what is the result each leaf should produce, I should say, and then how do I combine the result of two leaves internal.
Thank you.
Maybe a couple more minutes with that, and then we'll. From 418?
Yes.
Definitely need a bigger room.
I was thinking like half the.
Yeah,
I don't think so, to be
normal
honest.
people like
Because last semester there were 2 people who came. To be honest, the class was only 30 people, I think, and this semester it's 50. But I was like, okay, like that's like 2 more people. Like,
And just did assignment here.
If you want to work on the homework, that's fine, and just listen to me talk. I also am recording this, so if you're working on the homework and you just want to watch this later, also completely fine. Pretty well. I don't know how to book a classroom, so we have to figure it out. But it's fine. Okay, I'm gonna start talking about this just so we can say ish on time. We probably only will get to the first two problems, and then the third one, I'll just post a solution later. But it's also gonna be in the solution of this. Okay, so the goal here is to write a parallel version of, parallel version of computing the mean. So for all the reduced problems, the setup sort of looks like this sketch I have on the right-hand side. This is a really simple example with only 4 worker nodes, and those are here. Okay, so what happens in this setup initially? We start, this is, all of you taken CPSC 313 or like an operating systems hardware course. So you know about fork, the process in fork. So when you're thinking about the worker tree, this is how Mark's library works. We start with the initial process. It's going to fork a process. So the dotted line indicates that it's not a new process. It's just the same as the one above. And we get 2 processes, and then each of those do a fork. So we end up with 4, which makes sense. This is our worker tree. Each of the leaves are going to get some amount of data and run this leaf function. The way we get the data associated with a leaf is with worker tree get. Now, in my picture, we have values 1 through 8, and I've neatly split up the values 1, 2, 3, 4, 5, 6, 7, 8. You should often in your code worry about what if I have an empty list? What if I have a single hit list? And what if I have n amount of values? It's not necessarily going to be split evenly. So you should make sure your code handles all these cases for your data. Okay, so now looking back at the problem of mean, let's think about what we want to propagate from our leaves to internal nodes, and then how we combine that data. So anybody have a guess at each of the leaves? What operation should we do over each of these lists? What values should we send up the tree?
The mean of each list in the leaf.
So we could send up the mean of each. That's probably the first guess, right? So if 1 and 2, I take the mean, and that's 1.5. And 3 and 4 would be 3.5. The challenge is with these, how do I combine them to get the mean of 1, 2, 3, 4? Right? So, and I'm not really sure what that is, but it doesn't matter, right? Like, how do I combine each of the means from the leaves? So I'm not really sure that'll work. Maybe there's some math trick, but I don't think so. Anybody have another guess? It's related to sending out the mean. You almost compute the mean, but you don't actually do the division, right? The sum. We can set up 1, 2, sum to 3. And what else should we send?
The number of items in the list.
Exactly. And we can send that as like a tuple, right? And we do the same thing here, 3 and 4. So their sum is 7 and the number is 2. And I can repeat this, right? So that's what we do with a leaf. A leaf, we're going to send up a comment here. Then sum n. At a combined step, how would I combine the left child result and the right child result?
Just sum them and divide them by the sum of the number of lists.
Exactly. So you sum the sums and you sum the lengths. And that would give you like the total sum of 1, 2, 3, 4 and the length of 1, 2, 3. This would be 10, 4. Okay. And then we're also going to have some value from the right-hand side. That would be 5 plus 6 plus 7 plus 8, which is 6 and 4. And then what should I do at the root? The root is going to get, I should say, the combination of these. The root will get some final value that is the sum of everything and the length of everything. What do I do with that value to get the final result?
Just divide.
Divide, right? It's nothing crazy. 36 divided by 8, and that will mean whatever it is. And that is each of these functions. So the leaf, we compute the sum and the length. Combine, we combine the left sum, right sum, and the right length, the left length and the right length. Propagate all that. The root, as a final step, we have to divide the two numbers. So for almost every single reduced problem in the course, you should start with a setup that looks like this. What is my leaf function? What is my combined function? What is my root function? In the end, you call W tree reduce, W leaf combined root. Not too bad, right? So now we talked about the setup. Let's actually write a little bit of code. There's lots of ways to go about doing this for each of the problems. I haven't really given myself enough space. And hopefully the Erlang isn't the trickiest part. of the tutorial. Since you've had shaken off the leaves from the first homework, but regardless, I'll still write it down. So for the leaf function, we're gonna get the data from the tree. This you'll see all of the time, and it's helpful to just pull this out into like some sort of label. And then one way you can handle this is with a case statement. What are two possible patterns that I could have for this data? Or kind of what I hinted at here. Empty list, that's the one I need to worry about. How could I handle an empty list? One of my workers gets an empty list. I could say 0 and 0. What if my entire list is empty? Do I want the empty list to have a mean of 0? Maybe. It's kind of undefined, right? So I personally would prefer undefined, because if you have like no numbers, you divide by 0, it's like not really a number. But that's just an internal. Like if you were making this function, you're under the discretion to say empty lists are 0. I personally would say empty list should be undefined. To do that, we can return an atom. Just undef. And you'll see it a lot in the course again. And if you did it the other way, there's nothing wrong with that. You can leave your code as is. But this also is interesting because now we're going to handle the undef case all the way through, which is sort of interesting. You see a harder problem. And then in the other case, I have a list of any number of values. As I mentioned, I need to return two things. One is list sum of data. So that's just a standard library function that just sums a list. And then the length, which you don't even need to write this part for. In Erlang, you can just say length on a primitive, and it will give you the length. And I return that. And then you don't put a semicolon in the last case. You just write end, already has room, comma, and I think no comma here, comma. It's always hard to get it right. The Erlang syntax always gets it, but that's the leaf-ish. Any questions? Not too bad. For combine, I'm gonna erase this. Hopefully you have that down. Later. Combine. We have a function that takes two values. Left value and right value. I might call it just L and R. And then similar thing. Let's just case and pattern map on the cases. What cases do we have to worry about? Well, we're either going to return undef or a sum and a length. And so we have to handle both are undef, one is undef, both are a value, right? That's just typical. So we can say case. And then here I'm going to put L and R together in a tuple so I can do pattern matching. It's getting really fast. There's actually, I have a nicer way of doing this in my solution, which instead of writing another case on L and R, we can just have the function be defined on pattern matching. So you can do this with an anonymous function in Erlang by saying all of the cases directly. And then ending these two with semicolons. You've seen this before for like a function with a name, where you like literally define it multiple times, and then the arguments differ or the guards differ, and then you have like this really nice case version. This is just the same thing but anonymous. Okay, so as I mentioned, we can have the left be undefined. And we have the right value. We have the left be defined. And we have both values, which is going to be left length, right length. Okay. The reason I haven't written an undef case, you could and it wouldn't be wrong, is because in the undef R case, what value should I return? Just R, which if it's undef is also okay. If it's undef R is not undef, then it just works. Here, by symmetry, I return L. And then in this, where I have an ls, ln, rs, rn, pair of tuples, then I just, as we mentioned, return the sum of sums. So it's ls plus rs, and then the sum of lengths, ln plus r. And then would be a end and then a comma. Okay, so that's combined, 3 cases. And then the last one is just the root, which if it's undef, just returns undef. So that would just be a case like undef, undef. And otherwise, you would just take total sum, total length, and divide the two. I won't write it on the board because it'll take a while, but hopefully that makes sense. Okay. Okay, any questions about mean in the reduced form? So not too much different than a sum. Just some takeaways, right, is you want to think, what cases should my least return? Make sure not to forget about empty lists and singleton lists alongside lists of main items. And then your combine just handles all of the possible cases. Here I've simplified and cut down one case that's redundant, but generally speaking, you would have 4 since we have 2 possibilities at each solution, so 2 times 2. And you should be careful what you propagate. It's often not as easy as just like propagating the answer at each leaf and then doing whatever comes next. You often have to propagate some like intermediate thing and then do some final processing at the root. Okay, the next one is a slightly harder version. We'll start with the sequential version, which is largest gap is the problem. So looking at a list of numbers, return the largest difference between 2 consecutive elements. So you can see in the PDF, if I have an empty list, undefined, a singleton list that's also undefined because I have no neighbors. But if I have 1, 4, 9, 16, and 20, my gaps are 3, then 5, then 7, then 4. So my final answer is 7. And then the last example shows, if you have like a decreasing gap, quote unquote, if it's negative, that's fine. We were taking the absolute value. So my gaps are 3, then 5, then 5 again, and then negative 14. But the gap is 14, and so my answer is 14. So the first thing it asks you to do is write a sequential version of that, and to use a higher order function to do it. Just before you guys get into too much coding, what higher order function do you think would be appropriate? Or which one should you rule out? Like, it's definitely not map, right? Not producing a list. We haven't too many in the course, so some map. Other higher order functions could be. It's just a fold, yeah. If we're returning a single value, it often is a fold. So you want to think about what you want to accumulate as you go along, and then producing the final result. So give that a go first, and then we'll talk about code. Anybody still copying? Okay, so for the sequential version, let's talk about what we should accumulate. As we mentioned, you have to use a full del, probably other ways, but I think that's natural. The way I've set up my problem, and LGS is shortest for largest gap sequential. The first two cases are automatic, where they're like basically defined for you in the PDF. The really nice thing about Erlang is that translating a mathematical statement to code is extremely natural because it's like a piecewise function. You can write definitions very literally like this. The case you have to worry about, the interesting one, is where we have a list that is not empty or a singleton. We have 2 elements or more, and here I'm plucking off the head. Hopefully you guys have all seen this pattern before many times in class, like with count 3s and so on. A really natural way to get the front of the list in a function is to do this, and then tail contains everything else. Then I have a full del, which is, I've kind of given a hint away here. We're accumulating 2 values. So I have the current LM in the list, 2 values, that is my accumulator, my initial value of my accumulator, and then the overall full del is going to return 2 values as well, because that's what I'm accumulating. And the interesting one, the first one, is going to be the gap. So I've sort of given that away as well. The gap is going to be the first thing that we accumulate here. So let's start with that. What should the initial value of the gap be? Okay. Sorry?
You get a head, so that's.
So yeah, the gap couldn't be the head necessarily, because we're not saying like 0 comes in front of the list.
Yeah.
You could say in one version of this that there's always like a 0 on the front. But it actually should be 0, right? Because I don't know what my gap is yet. I know it's going to be strictly greater than 0. The smallest gap I could have in a list that's all the same would be 0. So we'll start with 0. I know there is going to be some gap. It could be 0, it could be non-zero, because I have more than 2 elements. So it's fine to not say undef. Undef would be wrong, or like make the question really hard to implement. But yeah, 0 is good. And then my initial value for the second thing, so here I'll also put, I'm going to write gap and then SF, and that should be familiar from like 110, gap so far. So the largest gap I've seen so far in the code. What is the second thing I should accumulate? What would be helpful to know?
Previous element.
Previous element, exactly. And so what would the previous element be on the first go around?
That's going to be it.
That's going to be the head, exactly. And this is previous. I'm pretty proof on that. All right. And then what should I do in the middle? What do I have to process? So I should probably compute the gap, right? That's not too bad. To do that, you can say gap, cur gap is going to be the absolute value of LM minus prev LM. Not too bad. I don't think abs requires any imports. Yeah, so abs is just available for you in the standard library. And then what do I propagate? Next line, I know I need to return the gap so far and the previous LM. Right, something like this. What would the previous LM be? LM, exactly, that becomes the new previous. And then what is the biggest gap so far? We have the current gap and the gap so far. So the new gap is the max, right? Exactly. Max. Gap set. And cool. Okay, any questions about that? That's the sequential version. You run some tests for that. So in solving like the normal recursion problems, just figure out like what you're accumulating, if it's a full del or map, whatever the function transformation is, and then just fill in the blanks. Not too bad. Okay, so now we have to use that to write a parallel version. In the parallel case, you should use code very similar to this for the leaf. So that's why this is kind of nice doing this first. And generally my advice for when you have a like reduced problem on a homework is start with a sequential version, because even if it doesn't, you can't use the code directly, it's often very similar to code that you'll use for each of the leaves, or at least computing like the value at this leaf, and then you propagate that. But we have to be more careful, right? Because like, let's take the reduced set from before. if I have like 1, 2, and I'll do like 4, 6, 7, 10, and 11, 15. So each of these have, one gap of 1, gap of 2, gap of 3, gap of 4. If I just propagate the gaps up the tree, I'm in trouble, right? Because if all I send is 1, here all I send is 2, here all I send is 3, here all I send is 4, I can take the max of these, and in this case, I'd be correct. But I wouldn't always, right? Because what if this was 1,000 and 1,004? Then this would still be 4, but obviously the gap between these is larger. So your problem with the parallel version is figuring out how do I propagate the gaps between two leaves and all the way up the tree, maintain that and combine the set. So start by writing a new leaf function. I would recommend copy and pasting some of the stuff we did with the mean parallel and write out, okay, I know I need to propagate my gap for sure, my largest gap, but I also need to propagate and start and end, right? Hopefully that's somewhat obvious. And then write out all your combine with a bunch of different cases, because now you're going to have a first, last. You also have to deal with these undefines for like empty and singleton lists, and combine that all with the tree. And that will probably take us to the end of lab. So spend a good amount of time on this, and if you get stuck, feel free to ask questions. But start working on the combine function the leaf function first, but then the combine function. Largest gap.
One solution to be considered.
Yeah, the whole solution, including some notes that I wrote for like how you would get to the solution code, hopefully useful.
Okay.
And should serve as a good base. I know the probably worst thing about all these reduced problems is the syntax. It's really gross, so. No worries.
So how the size of the subproblem like determined, like it's like set two or it's fully.
The size of the subproblem. You mean like at each leaf?
Yeah.
Could be anything. Could be empty, single, or and the example I had was all twos. You're right, but that was just for illustration.
It's not usually equally divided.
I mean, we would want it to be equally divided, but you shouldn't assume the library does it. And you'd want it equally divided, right? Because you have all the workers that work at the same time, like it just makes sense.
Efficiency, yeah.
Yeah, but you shouldn't guarantee it. Just in case people are stuck on the leaf, I'm going to talk really quickly about how you can change the sequential version to work for this. As I mentioned before, we have to deal with these like other cases, and we need to propagate more information about this list. So there's only a few slight changes you have to make to LGS. I'm calling it LGS star, and then you can use it, the sequential version as the leaf version. The first one is this line. So when we have a singleton list, I can just name now, it's value V. I can just propagate undefined because V may be a part in combination with other leaf values as a part of the largest gap. So instead, I can propagate some tuple containing both. So I don't have any gap, so I still have undef, but I do have a value. So there's that. And then for the case where I have a full list, what needs to change? Well, one thing I want you to think about first is that the result value of list full val is the largest gap. And the second value, which I ignored initially, is the final value. This you can call it the last value. Being split. And I'll definitely need to propagate that. On top of the last value of a list, I also need to propagate one other value. The first value, right? And so this final line gap now becomes head, the gap, and last value. And that's what I propagate now instead. So you can see in the base case, I have no list, just undefined. If I have a single value, I propagate that value undefined. You can treat it like the first or the last value in my code of first. And then when I have a list of two or more items, I propagate the head, gap, and the last value. And then the interesting bit is how do I handle all of the combinations of these things to make it work? So you have about, I don't know exactly how many, but you have quite a few. In my version, I have 6. So some of them are easy, right? Like if the left side is undefined, the right side is a value.
Mhm.
For example. So we'll go through case by case. The root function isn't too bad. You basically just propagate the max if it exists, right? So if I get a value that looks like this, or a value that looks like this, obviously I have a singleton list or undefined, like an empty list for my whole list. So I just return nothing. But if I have the max, I just return the max. So I'm not going to write root if that's not too bad. This is the interesting stuff. So in my version, I have 6 cases. One where either side is undefined. This is just like mean parallel. We just return the other side. If both sides are undefined, neatly, this returns undefined. Otherwise, we just worry about the other side. So R, and this is vectors. Yeah. 2 down, a lot more to go. The next 2 cases I have is where, or let's do the next case actually, where I have 2 singleton lists being combined. So the left side had a value, the right side had a value. Now I need to propagate something. In this case, what do you guys think it should be? One thing with reduce is that you can assume that the left child is values on the left side. You have to worry about like the children being like swapped or anything. You should keep in your head that like the left values are like literally to the left. So in this case, we exactly have something like this, this, and we need to propagate the correct results for a list like this. Right. So what should this look like? Again, we're always returning something that's like front of list, gap so far, end of list. So the front of list is what? The left value. The gap so far is just exactly the gap, which is taken from this line. The absolute value of L minus R, and then R. Okay, another case down, so where to go. These 2 are symmetric. It's just saying the left had a list that was greater than or equal to 2 items. The right side was a singleton, and then vice versa. In this case, what do I do? Not as easy. What do I know for sure is the front and end of my list? Yeah, LF for the left front, and R is definitely the end. What is my max going to be? Like, what values can I compare?
L gap and then gap between.
Exactly. Super good. So we're going to take the max of 2 things. One is my L gap, which you can kind of think of like my gap so far, except I only have one from my left side. And then I also have to consider the gap between LL and R, which is nice. Visually in the code, you can like see like these are the things that are close together. And in this final case too, where we have like 2 complete lists, the only values we have to compare are the ones that cross the boundary, right? LF is all the way on the outside. It has no left neighbors, no gap. RL, the right last value, has no neighbors. But we do have to consider there was a gap here that we missed in the reduce. So the same idea here, except R was just a singleton. And so we take abs of R minus LL, and we take the max of these 2 things, and that's our gap so far. We do almost the exact same thing on this next line. Here. So this becomes, again, L, the max of my R gap, and the absolute value of what things would boundary here. You can't see it as nicely, but RF and L would be beside each other, right? So we take L minus RF. And then my rightmost value is still RL, the last value of this. Cool. And then in the last case, it's really similar to what we've been doing before. You can already see the first and last value. That is LF left front and RL last value right. I really should have used like front and back. But and then in the middle, I have to take the max of these gaps and the new gap. So when you see it like this, hopefully it feels somewhat less bad. I remember when I saw this problem the first time, I was like, this is really hard. But the thing that makes it easy is if you worry about the leaf first, then think about all the possible cases if you're combined. And these cases that I wrote out might not have been obvious immediately. So if you want to instead write out like all of the possible cases, literally, like you have 3 different things that were returned here, times 3, you'd have 9 things here. That's not a big deal. You could write out all 9 and then see that if you could collapse together. Sometimes your like linter might even check that you can collapse cases together. So let it. Just write out all 9 and then do it. That way you don't think on like an exam. But again, this is what the solution has. I want to jump to that. So okay. And then we take the absolute value, like I said, of LO. So that's a reduced version of the largest gap. Not a bad problem. Hopefully it made sense. We still have 4 minutes, so not really a lot of time. In the PDF, there's a follow-up that is slightly harder. It involves some math. It's the function polynomial that takes a given polynomial with some coefficients and evaluates it at x equals to b. The trick, just very briefly, for when you hopefully try this before the first midterm, is that you can factor the equation, right? If you look and you imagine like the left-hand side and the right-hand side, if you factor out a power of like x to the k, then you have like the same thing on both sides. And when you combine them together, you can just multiply the power from the left-hand side to the right-hand side, or I think the right-hand side to the left-hand side, and then you can combine them. So the trick is sort of noticing that multiplying by powers, like if I have, it's a sketch that I did here. So if I have something like, so f at b of a naught plus 1 at b plus dot 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 plus a k at b to the k is going to be like, imagine like the left-hand side. And then the right-hand side, we're going to sum, is going to be at k plus 1, b k plus 1, plus a n, b to the n. Then, yeah, you can factor out a power of b to the k out of these terms. And so if you compute this and pretend it's at this like base, then all you have to do is raise this to b to the k. And then you can treat this, you need the right coefficient, but you can treat these like they're the normal values. B0 over b and minus k, which is k. And so your combined step, you're going to take the length of values you've seen so far and just multiply b on the left times the other right. So nicely done. Hopefully that makes sense. There's a sketch of the math included in the notes of the solution. So you get stuck, you can cheat and look at that markdown file without looking at the actual solution, and then the code is there as well. Cool. So that's going to wrap us up for lab 1. I will stop recording.